Hello, this is MA 259, Differential Equations, and we're going to talk about Section 5.2. I encourage you to read through Section 5.2, the instructions, but my goal here is to work out some of the problems, specifically in this case, problem number 1, and give you an idea of how you should work out the problem as well. So this is section 5.2, number 1. We are given a system of differential equations, x1 prime equals x1 plus 2x2, and x2 prime equals 2x1 plus x2. What I like to do is write this system of differential equations as a linear algebra matrix style system. So I have x prime as a vector equals the A matrix, and the A matrix comes from the coefficients of each of these equations, 1, 2, 1, 2, 2, 1, 2, 1. And that's times x vector, and x vector is x1 and x2. Then I write over here why A matrix is 1, 2, 2, 1. To find the eigenvalues, what I need to do is find the determinant of the matrix that results from A minus lambda I. So I find A minus lambda I, take its determinant, and set that equal to 0. Now the theory of why we were doing that is in the lecture. It is not in this particular video. Under the circumstances, we do not have the time for the lecture. So you please read about that in section 5.2 in the notes. Okay, so the actual nuts and bolts functionality of how we're doing this. I take A minus lambda, remember that's a constant, that eigenvalue lambda is a constant not equal to 0, A minus lambda times I, which is the identity matrix. And when I simplify that, I get 1 minus lambda, 2, 2, 1 minus lambda. Now I find the determinant of that resulting matrix and set it equal to 0. When I do that, I get 1 minus lambda times 1 minus lambda minus 2 times 2, and I set that equal to 0. When I simplify the algebra, I get lambda squared minus 2 lambda minus 3 equals 0. I factor and find that lambda is equal to 3 or lambda is equal to minus 1. This is the case where you have distinct real eigenvalues. They are distinct, they're different, and they are real eigenvalues. The case of distinct real eigenvalues. So on each separate eigenvalue, I then perform the following. For eigenvalue lambda equals minus 1. I plug in the associated eigenvalue into my A minus lambda I equation. So this is 1 minus minus 1, 2, 2, 1 minus minus 1, which simplifies to 2, 2, 2, 2. So affect what I'm doing then as solving the system of 2, 2, 2, 2 times the eigenvector v1, v2 associated with this eigenvalue negative 1 and setting that equal to 0. That's that solving the system A minus lambda I equals 0. Again, the theory, this is not the same as the determinant of A minus lambda I is equal to 0. This is A minus lambda I times the vector lambda equals 0. Again, that's some theory that is not being covered here. So the nuts and bolts is I set up this A minus lambda I with the associated eigenvalue and the associated eigenvector, which I don't know yet, equal to 0. And then I solve for v1 and v2. So I can put this in a reduced row echelon form matrix, 2, 2, 2, 2, with the augmented 0, 0, and get 1, 1, 0, 0, 0, 0. And so now I have an over-determined system, so I have a free variable. So effectively what I have here is 1 times v1, 1 times v1, plus 1 times v2, plus 1 times v2, is equal to 0. And then my v2 from the second line is equal to a free variable, which in this case we're going to call c. So v2 is a free variable, which in this case we're going to call c. So then if I set this to the situation where v2 is being moved over to the other side of the equation, I get v1 equals minus v2, and that's equal to, since v2 is equal to c, v1 equals to minus v2, which is equal to minus c, and v2 is equal to c. So now I have an eigenvalue, v1 and v2, that's eigenvector minus c, c. And I need to choose an appropriate value that makes that true. Well, since c is c, I'm going to choose 1. I could choose 1, I could choose 2, I could choose 3. I can't choose 0, because remember, the vector can't be the trivial vector 0, 0. But I chose 1 here. That's the simplest one. So I get minus 1, 1. So the associated eigenvector for the eigenvalue lambda equals -1 is -1, 1. Then my first solution then to this differential equation system is x1 of t equals -1, 1 eigenvector times e to the minus that comes from the eigenvalue t. So raised to the minus 1 t. Now for the second eigenvalue. For eigenvalue equal to 3, I plug in 3 in for lambda, 1 minus lambda, 2, 2, 1 minus lambda, and I get minus 2, 2, 2, minus 2. So what we're really talking about then is the system with the associated eigenvector, v1 and v2, associated with lambda equals 3, minus 2, 2, 2 minus 2, times v1, v2 equal to 0 vector. And notice what I did in this case was something a little different. I put A and just did the reduced row echelon form of A without this augmented zeros like I did up above. So I left out this right-hand side. Well, the reason I left out that right-hand side is that is always just the same values over there. That'll always be 0, 0. So I don't bother typing those in, because when I do the reduced row echelon form, it's just going to turn out with 0, 0 over here on the right-hand side anyways. So I don't bother with that. I know how to interpret what this value means. So I have 1 v1 minus 1 v2 equals 0, and my v2 is free, which I'm going to call a constant. So I solve this for v1, and I get v1 equals v2. I moved this over to the other side of the equation, v1 equals v2. And since v2 is equal to c, I have v2 equals c, and v2 equals c. Then I choose some value for c that makes the statement true. And c equals 1 is fine, so I get 1, 1. So for the eigenvalue, lambda equals 3, I have the associated eigenvector 1, 1. And then I get x2 of t equals 1, 1, e to the 3t. So the solution to the system of a differential equation is x of t equals c1 times, this is a constant, times x1 vector t plus c2 times x2 vector t. So c1 times the x1 and c2 times this x2. And then I prefer to write it out, so I have c1 times the x1 and x2, and this I consider to be the answer. Now, some people, and in some books, they're going to actually write out the system. And so this is written in the nice vector matrix style. But some people are going to write it out. And so they're going to have x1, which comes from this x vector, x1 of t equals, and then minus c1 times e to the negative t plus c2 times e to the 3t. And then x2 would be c1 times e to the t minus t plus c2 e to the 3t. Now remember, we had the situation of the free variable. So I could have chosen, for example, minus 1 to be my eigen vector. So I could have chosen this c to be minus 1, and then I would have had 1 on top and minus 1 on bottom. And if that were the case, down here in my solution, this would be 1 on top and minus 1 on bottom, and my solution would be 1 here and minus 1 there. But remember, because those are parameters that we don't know, until we're given an initial condition, those will take on different values depending on what you choose to make the system work. Okay, so what you're going to be asked to do is a similar type of problem, and write out the solution and scan it, or take a picture with your cell phone and submit it via Blackboard.